So I'm Radia Perlman, and so I'm doing this tutorial, and the slides are already up someplace. I assume it's not too hard to find them. Anyway, and we decided to post PDFs before we'd been posting PowerPoints. If you care and want the PowerPoint, just send me email and I'll send you that. I don't care about format unless I'm trying to read somebody else's format and I don't happen to have the thing that reads it. So, okay, so this is the point of this tutorial. Oh, yeah, this is not about looking at all the bits and bytes and details of any particular protocol. It's also not about telling you there is one right way to think. Instead, what I'm trying to do is to say, well, okay, what are all the various things that need to be solved at this layer? And for each sort of conceptual separate piece, we say, oh, I'm not loud enough? Okay. What? Oh, okay. Is this better then? Okay, so for each conceptual piece, we say, well, here are the various different ways that different things can differ, and here are all the pros and cons of them. And I intend it to be thought-provoking. I'm not filling you with the right answer. It's more like a philosophy of how to think about these things and how to actually, when you have competing proposals, how can you actually compare them? What's actually different about them? Also, I'd like to suggest some areas that can be researched. A lot of the ways decisions are made are based on who is the loudest proponent, which is not necessarily, kind of the right technical answer. It would be good if somebody could actually study it and see whether things actually behave the way people think they might. And hopefully this way of thinking will also apply in other protocol areas. So all opinions expressed herein are mine alone, but I'm sure a lot of people agree with me. As a matter of fact, I've been trying these arguments out on people, and I haven't been able to find anyone to come up with anything they disagree with. So, and I'm also attempting to find complete arguments on all sides of things. So if I've left anything out, please tell me, because that's one of my hobbies, is sort of collecting all possible arguments on both sides and understanding them and understanding trade-offs. So let's start with, this is layers 2 and 3. What are layers 2 and 3? So yeah, OSI came out with this notion of layers, which is a good way to think about networks, but nobody actually follows it that way. So it's really just kind of a way of thinking about them. But my view of network layers, which is kind of based on the OSI model that everyone's seen, is layer 1 is the physical layer. It's like, how do you signal a bit? What does the cable look like? Layer 2 is neighbor to neighbor. That means how do two neighbors talk to each other over the same cable? So you have to be able to, you're sending bits, and somehow you have to signal among the zeros and ones that this is the beginning of a packet, this is the end of a packet, this is a checksum. That's what layer 2 does. Layer 3 is the thing that creates an entire path and forwards packets along a path. Layer 4 is called transport, which always bothered me, because to me it's layer 3 that's transporting 3 things, not layer 4. But at any rate, layer 4 is the thing that's end-to-end, where the endpoints on either side might number the messages and put them back in order if they got reordered in the network, or retransmit things that got lost. And layers 5 and above are boring. That's why it's Perlman's view of networking. So, some mysteries. What does it mean? People argue about, should we forward at layer 2 or forward at layer 3? What kind of question is that? Especially if you look at the definitions of the layers, you shouldn't be forwarding at layer 2. That's what layer 3 does. But I'll explain in here how that came to be. And why do switches have to worry about keeping packets in order? The whole reason for TCP was so that, well, you know, the network will lose them, they'll put them back, you know, they'll get out of order, and then at the end point you put them back in order. And one of the things that I find really annoying and quite ironic is that because TCP implementations freak out if it gets packets out of order and behave really badly, then you can't sell a network switch that doesn't stand on its head to try to keep things in order. And oh well. So what is routing? So data gets put into an envelope, and the envelope is the thing that the network looks at to decide where to deliver it. And there's some information in the envelope that I'm going to call X here, because I'm going to, in a few slides, I'm going to talk about different kinds of information that can go into X and the implications on the switches or routers. By the way, I am absolutely using switches and routers and bridges. All those things are interchangeable. They're just things that forward packets. So in the envelope, you put this piece of information that I'm calling X, and it tells the switch what to do with, well, it tells the switch in coordination with a table that's at the switch. The switch looks at X in the envelope, looks at its forwarding table, matches up the entry corresponding with X, and makes a decision as to how to go. Now, this might seem like really, really basic, but anyway, so a forwarding table has all these different values for X. You look at the envelope that you got, you match it up against which entry there, and it gives you a set of ports that are reasonable to forward to for this particular X. And then I'll talk about what kinds of X there could be. So the basic components are what information is in the header of the packet, what the forwarding table is indexed by, meaning what is that X thing, how the forwarding table is created, and the basis for spreading traffic. So if you have a bunch of different choices for forwarding for a particular X, how do you choose which one of those to use? So the forwarding table takes your data, the mysterious X thing in the envelope, it looks at that, finds the corresponding entry in the forwarding table, and it tells it which way to forward it. So now I'm going to talk about network protocols. A lot of what everybody knows is indeed false. It's the way networking unfortunately tends to be taught is as if, you know, memorize these RFCs. It gives you the impression that, you know, TCP/IP arrived on tablets from the sky in its awesome perfection. Nothing else ever existed. If a book, you know, mentions anything ever done by any other standards body, it's only to kind of sneer at what morons they are. But you know, this is not. So I tell people that, you know, like network protocol stuff tends to often not be, you know, like considering all the various pros and cons of different conceptual approaches, but more like drunken sports fans, where it's like, rah, rah, our team. And that's not the best way to really understand what's going on. So things are so incredibly confusing. One of the things I really like to do is when I hear about A and B, I like to really understand what's at the heart of these things that make them different and what are the pros and cons. This is not an easy thing to do because you're presented with two 600-page specs, all with their own acronyms and you know, arcane terminology. So you try to save yourself some work and you go up to somebody who's a proponent of A and you say, how does A compare with B? And they say, well, A is awesome and B sucks. And then you ask B people, you get the same kind of thing. Somebody mumbles some sort of vague marketing thing, and then everybody starts repeating it, and then you feel really stupid for questioning it because you've heard it so much, but a lot of times there's no actual truth to it. But also, A and B are moving targets in the sense that if you tell an A proponent about a feature in B that's better, they'll just steal the idea So A is not what it was at any point in time. It's just, you know, whatever. So that it's, I want to separate out from, you know, giving a name to a particular thing and talking about which team it is, and instead just looking at the various conceptual pieces by which things can differ. So, yeah, I try to ignore buzzwords and which team things are on, and I also like to question assumptions. So whenever people say, this is the way things are, I like to think about it and say, does that make any sense to me? And right. So one way that people like to compare things, which sounds like it's really great science, is you measure it. So if you're trying to compare technology A and B, what you do is you measure A and B according to how much power is used or something. I'm never going to believe a measurement like that unless I can understand something intrinsic about the technology of A versus B that should make that measurement make sense. Otherwise, the only thing that you're actually measuring is one implementation of A versus one implementation of B. So even if you measure A and it's twice as much power, it could just be that that implementation was not a very good implementation. So in what ways can networks differ, and we'll talk about them here. It's what is the X that's in the envelope of the packet, who computes the forwarding table, whether the forwarding table is always complete so that when you receive a packet you know immediately what to do with it, or whether when a conversation starts up, at that point you have to add entries into all of the switches tables so they'll know how to handle packets for that conversation. Whether a switch is allowed to choose among multiple next hops for the same X, or whether you know, someone tells it exactly for this type of packet one way to go. And then there's how to translate from a layer 3 to a layer 2 address. So a flow. This is, you know, terminology, people use it in different ways. This is sort of how I'm going to use it in this particular talk. A flow is a conversation between two applications. And usually networks attempt to deliver all packets for a given flow in the same order in which they were sent. So if there's two different applications in node A that are talking to two different applications in node B, you don't have to keep those in order with respect to each other, but the one application talking to the other application wants to see the packets in the same order that it was sent in. So a flow is sort of a conversation that starts up. And in a packet, usually switches say, oh, this is in the same flow, if it's not only the same destination address, but it's also the same source address, the same protocol type, and the same TCP ports. And then bridge, router, and switch is something that forwards packets, and I'm mostly using them interchangeably. Usually when people talk about things that forward Ethernet packets, they call it a bridge or a switch, whereas if they're forwarding IP packets, they call it a router. But it's, you know, not really an intrinsically different type of device. So, okay, what's in a packet? So first I'll talk about there's different types of addresses. So one type of address I'm calling a flat address, and the other is a hierarchical address. So a flat address is something like Radia Perlman. Wherever I go on Earth, I am the only Radia Perlman. And it would be really nice if you could send me a letter by putting in the envelope Radia Perlman, putting it into a mailbox, and the post office will always be keeping track of where I am. Well, you know, obviously that doesn't work very well in terms of the internet, but in terms of a fairly, you know, some size cloud, it's very nice if you can move around within that cloud and keep your address. So that's when it's sort of very convenient to have a flat address. It's admittedly it won't scale to be able to support the entire internet, but it does scale probably within 100,000 nodes. As a matter of fact, the cell phone network seems to be kind of flat addresses. You can go anywhere in the world and keep your cell phone, though I guess it's a lot more efficient if you happen to be where you got the phone. With a flat address, there's two kinds of flat address that I'll talk about. One is where the addresses are handed out in a dense way, 1, 2, 3, 4, 5, 6, in such a way that the forwarding table can be very simple. You can just look at the address, and if it's a 7, you look at the 7th entry into your forwarding table. The alternative is something like Ethernet, which has a flat address. It's a 6-byte address, and yet it has nothing to do with where you are. No matter where you are, you keep the same 6-byte address. Your forwarding table might need to have as many entries as there are Ethernet addresses in your cloud, but it can't be a simple direct lookup because 2 to the 48 is like a very long table. So instead, you have to hash the 6-byte thing to go into one of n buckets, where your forwarding table has n buckets as its entry. The other kind of address is hierarchical, where it's kind of like the way you mail a letter, where you say what country it is, and then what state it is within the country, what city it is, and so forth. Where if you're not in some other country, all you have to do is look at the country part of the address and say, oh, that doesn't belong in this country, and you get it to someone that knows how to deal with the other countries. So it means you don't need to have that many entries, because everything inside that other country can be summarized with one entry, which is that country. Now, you could either do it with fixed hierarchy, where you say in your address, you're going to say that 6 bits are going to specify which country it is. 7 bits will be which state within the country. And that's convenient for the switch, but it's not as flexible, because it could be, like if you look at telephone networks, some countries have very, very small telephone numbers, very short, because there aren't that many telephones in the country, so you don't need to dial as many digits. So it, likewise, it might be more convenient to be just completely flexible, but then the switches have a more complicated decision to do to be able to find the forwarding table, and I'll show algorithms for how you can do that. So terminology I wish people would use, but they don't, is that an ID is something that doesn't change if either the target or the source moves. So an ID or an identifier. Whereas a name, the way I would use a name is that it's like an ID in that it doesn't matter where you go, you keep your same name. But it's, instead of an ID, it's a human-friendly string, whereas an ID is more of a number that's convenient for a computer. An address is something that changes if the target moves, but the same address should work no matter who is using it. So, if I move, my address changes. But whatever my address happens to be, somebody in Tibet should be able to use the same address to get to me as somebody in California. And a route is something that changes if the target moves. So a route is something like go 2 blocks west and then, go 4 blocks east and whatever, which obviously matters where you're starting from. Unfortunately, people use the term address the way I use the term ID, I think, because an Ethernet address, everyone calls it an address, whereas I definitely would call it an identifier, but at any rate. So the Ethernet address they call a MAC address, and that's another whole story as to why it's called a MAC address rather than an Ethernet address, but anyway. So a flat address means it's not location dependent, which means, as I said, I would have called it an identifier. Flat is very convenient, especially in clouds where you have virtualization, where you want to be able to move virtual machines around to different servers as the server gets overloaded, or if it's underloaded, you may want to consolidate things. So it's very convenient if you can move things around and without having them change their address, because it has implications on protocols and other layers if you suddenly change somebody's address. And also it helps for us auto configuration. You know, if you can keep your own address around, it doesn't have to be a human that has to think about it and changes what your address is. But if the entire internet were based on flat addresses, the forwarding table would be too large. So, you know, this is what the forwarding table looks like. There's two types of flat addresses, as I said. Dense, where the address, if the address is 6, you find the 6th entry in your table, and sparse, which is like the 6-byte Ethernet address where you have to do a hash in order to find the forwarding table entry. So yeah, if it's a sparse flat address, you have to first go through a hash function, which then tells you which bucket in your forwarding entry gives you which way to send the packet. So Ethernet addresses are kind of interesting. The technology was invented to hook maybe 1,000 nodes together, like within a building. And it's kind of very strange in a way that they chose a 6-byte address for something that was only intended to hook 1,000 nodes together, because you know, 2 to the 48 is a lot bigger than 1,000. So why did they make it so huge? And the reason was that, and it's actually one of the reasons Ethernet is kind of so easy to use, is that the address is created when the device is manufactured. Each device that can plug into an Ethernet has a unique 6-byte address that the manufacturer puts in, and then all you have to do is buy a device, plug it in, and it automatically has this unique address. So you don't have to configure the addresses when you're putting a network together, and that's you know, a very nice usability feature. The structure of the Ethernet address, it's 48 bits. The top 24 bits is known as an OUI, which stands for Organizationally Unique Identifier, for those that insist on seeing acronyms expanded. It's assigned by IEEE. There's 2 special bits inside the OUI. One is whether it's a group address or an individual address, or whether it's a multicast address or a unicast address. And individual address will be something that will be born with the device. A group address is something that tends to be in a protocol spec that you say, if you want to talk to all the nodes that speak this particular protocol, then you send it to this particular group address. Another bit is whether it's globally assigned or locally assigned. So if you actually buy a block of addresses from IEEE, that bit will be set to be globally assigned. And if you want to use any addresses that are not assigned, you're welcome to use any of them. You just have to set the bit to be locally assigned, but then you have to be careful because lots of different organizations have their own proprietary uses of these, and you may wind up using the same address as somebody else. But if you get a globally assigned OUI, then that gives you 24 bits, or 2 to the 24 devices that you can manufacture, each with its own unique ID. Oh, and all ones is intended to mean broadcast. It always drives me crazy when people try to, you know, correct me when I'm saying broadcast or multicast. To me, they're the same thing. Broadcast, in theory, means everybody, and multicast is some subset. But to me, there never should have been this concept of everybody, because there is no protocol that everybody wants to listen to. But anyway. So just a trivia thing. Originally, when they were thinking of 6-byte addresses for Ethernet, some people were saying, you know, that's big enough that for the size of the networks we're talking about, as long as you have a good random number generator and you choose your 6-byte address randomly, the probability of error where 2 nodes wind up with the same address is smaller than the probability of people getting it wrong when they're manufacturing it. So that would have been a cute idea, but you know, there would have been a problem that people would not have bothered having a good random number generator. So okay, hierarchical addresses, I've kind of explained. You know, if you're outside of a country, you don't have to know about the structure of the country. But even if you're in the same country, if it's a different state, you don't have to know about the structure of that state. You just get it to that state and then let the forwarding structure inside that state know where all the cities in that state is. So it allows your, doing addresses hierarchically this way is nice because it means that the forwarding table can be much smaller. Many addresses can be all summarized in the same forwarding table entry with the same prefix. If you assume that country comes before state, it's the prefix. So with hierarchical addresses, if you're careful about how you assign the addresses, then a whole blob can be summarized with a single forwarding table entry. So this whole blob here, everything starts with a 2. But if you're inside of this blob, then you have to know that to get to 2.7, you have to go to this blob, and so forth. And as I said, you could have a fixed hierarchy where the switches know that there's separate fields. You know, 6 bits say which country, and then 7 bits say which state within the country, which would make the switchers a little bit simpler than having to do this find the entry, to find the prefix that has the longest match to the destination address. So if you're trying to do this longest prefix match, there's basically 2 algorithms for doing it. One of them is TRIE, and I'm not sure whether it's pronounced tree or try. It was, and the other one is a modified binary search. So just to give you kind of an intuition for how you can do this. With this algorithm, let's say that in your forwarding table, you have these prefixes. The null string, which actually matches everything. So it's sort of known as the default. If you don't know where else to do it, send it to a guy that is advertising that he can reach the 0-length prefix because he can reach, that means everything. Then there's A, ABC, ABCDEF, and these are the entries. And yeah, that's probably one of the things suboptimal the projector was yelling at me about, because there's other things that are not on the slide there. So you start out, the way you have to create this, the switch has to create this data structure out of the prefixes that it needs to organize so that it can find them. And the way that it does it is it starts with the null string, and it puts a star here if that string is actually in your forwarding table, if it's one of the prefixes. So since the null string is, it puts a star up there. And then what is the next possible character that can be? Well, all of the strings start with an A, so the only arc leading out of that node is an A, is labeled A, because you don't have anything else, any of the things in your database that start with anything but A. Okay, A is also in your database here. It's one of the prefixes, so you put a star there. And now if you look at the other prefixes, some of them start with B, and the things that are off the screen start with a C. So therefore, out of A, you can either go to B or C. And AB is not in the table, so there's no star there. So you've created this, this database, data structure for searching for things. Let's search for, let's say that you had a data packet that had ABCD. So let's see how you would search this. So you'd start with the null string and you say, great, the last time I saw a star was at the null string. But the next string, it's ABCD, so you see A, and then that one also has a star, so you can forget about the null string, because A is a longer match. So now you got to A, and next one is B, and AB is not in the thing. So you have to still remember A was the last time I saw a star. So I said it was ABC. You get to ABC, there's a star there, so you have to remember ABC. And then there's D, and yes, indeed, there's an arc there, but there's no star next to that, and at this point, that's the end of the string. So ABC is the longest matching prefix. Another way you can do it is binary search, which what you do is you sort of create ranges. So if you have the entry A in your prefixes, you create two numbers. One is A with padded out with all ones, and the other is A padded out with all zeros. And so you do this for each one of them, and you sort them, and you wind up with a data structure that looks like this. I do not do pretty PowerPoint, so I am really sorry. So the null string winds up being two numbers, all zeros and all ones. The prefix A winds up being A with all zeros after it and A with all ones after it, and so forth. And if you sort them all and kind of think of there being an arc between the first and last number there, then depending on where something fits, so if something were to fit right here, that would mean this is the longest matching prefix for it. If it fits in here, then ABC is the longest matching prefix. Is that sort of understandable? This is the first time I tried actually describing this particular algorithm in public, and a lot of people have jet lag and whatever, so if some of you actually got it, then it means that my picture is plenty pretty enough, I guess. Okay, so summary of how addresses can differ. You can have it be a flat address, which means you move around and you can keep your address, and if it's flat, it can be either dense or sparse, or it can be a hierarchical one. And hierarchical scales better by allowing everybody within the same blob to look to occupy only a single forwarding table entry. So another possibility that you can put into a packet, I'll call a label. Now, what is a label? A label is something that changes hop by hop. So the label is only of significance on the link between two routers. And so your forwarding table in a switch that's doing it based on an X that's like a label, the forwarding table looks at the packet, sees the label, and looks at the pair, which is which port it came in on and what the label was. And the forwarding table will say, if it came in on this port with this label, then you need to forward it onto that port and change the label to this other thing. So why would anyone do that? What are the pros and cons of that versus an address? So this is how the label thing works. So the forwarding table at R1 says that if it gets something on port 3 with label 51, I need to forward it out port 7 and change the label to 21. So the particular path we are going to focus on now is the path from A to D. And the forwarding table entries in R1, R2, and R5 related to that are in bold. So R1 has a forwarding table entry. Apparently, for this path, A is supposed to send a packet and put into the header 8. That's all it needs to put into the header because that defines the entire path. So 8 forwards something to R1 with, in the header, it says 8. R1 looks at its table and it says, if I get something on port 4 with label 8, then I need to forward it to port 7 and change the label to 92. And then on this on this link over here, R1 has forwarded, changed the label to 92. R2 sees something coming in on port 2 with label 92, and its forwarding table says I should send it out port 4, and I should change the label to 8. And R5 says if I get something on 1 labeled 8, then I have to forward it out port 3 and put a 6 there. So that, you know, if you're kind of remembering the, you know, the which teams kind of thing, this is how MPLS works. So originally, why would you do it with labels? Well, it was originally designed that way for telephony networks, where if you think of the telephone network, you have zillions of telephones attached to the network, but very few of them are actually talking at any point in time. So if they had put into the header the address of your telephone, it would have been a much bigger label than if it's the particular conversation going on. So what would happen when you dialed the phone is that the telephony network would set up a path by assigning the labels at each hop, and then for the duration of your call, you would be able to use this much shorter identifier. But that only works if the total number of pairs talking is much smaller than the total number of nodes. If you want every single pair of nodes to be able to talk at any point in time, your forwarding table would be the square of the size if you used, you know, kind of a label than if it were just a destination address. So the reason it made sense for ATM, which was a telephony kind of thing, was because of two reasons, two assumptions that are not necessarily true in today's networks. One is that, as I said, the total number of nodes was a lot bigger than the number of pairs that are currently talking to each other. And the other assumption was that it was perfectly acceptable to incur latency while you set up the path between A and B. You don't expect with the telephone to be able to start talking. You expect to first have this connection latency. For IP, the reason MPLS sort of looks like that was it grew out of this concept that was known as tag switching, when there was kind of a while when people were thinking, oh, this longest prefix match for looking at IP headers, oh, that's so hard. So what you do is when you receive a packet from a neighbor, you say to him, hey, would you do me a favor? And in the future, when you're sending me this packet, put this extra little you know, hint at the front of it, which is this tag that which is a number I've chosen that will help me find it more easily than having to parse the whole thing. And then since each guy tells its previous neighbor a number, that's why it's something that changes hop by hop. Now, people tend to assume, because they've been using MPLS for what's called traffic engineering, which is to set up a path between A and B. So there's, you know, one customer that you want to guarantee them a certain amount of bandwidth, so you create a path. You could do it that way, or you could do it with a destination-based way as well, where the label doesn't change hop by hop, by just creating a step forwarding table entry, you know, for a special destination. So, you know, it isn't anything intrinsic in this label swapping that makes it any better for traffic engineering than something where it would be based on a destination address. So, yeah, destination-based versus label-based, it seems that destination-based, your forwarding table will be much smaller. It's only on the size of the number of destinations rather than the square of the number of destinations if it's an entire path between two nodes. With the you know, label-based thing, if you want to do it like telephony and create an entry when A decides it wants to talk to B, then you have this latency of having to set it up before A and B can talk. Okay. So now a different topic, which is keeping packets in order. which me as a layer 3 person, I just think that we should have said just say no when people said that, you know, we had to keep your packets in order. You know, I think the end nodes should just, you know, that layer 3 should be allowed to do that. But at any rate, implementations, there's kind of this chicken and egg problem, that because implementations behave badly if you give them packets out of order, your switches kind of have to make sure that they keep them in order, and because the switches go on, you know, go out of their way to make sure that things stay in order, implementations can get lazier and lazier because they know, oh yeah, we don't have to worry about packets getting out of order. But anyway, you know, I believe a network would function a lot better if switches could just, whenever they see a packet, if they have a set of ports, they put it on whichever queue is shortest, but whatever. Yeah, you have to keep packets for the same flow in the same order because either end node protocols or implementations of protocols. So for instance, TCP could deal with out of order, but it's really the implementations that have gotten lazy because you have to do sort of fancier buffering. But one kind of nice thing, if you know that the network is keeping things in order for you, then if you receive packet n and then you receive packet n plus 2, you immediately can know that n plus 1 probably got lost. Whereas if packets are allowed to sort of wander around on any path they want, then you have to do it based on a timer, and it might take longer for you to let the source know that it needs to retransmit things. So, you know, there's a plus side to having the network try very hard to keep them in order. But we do want to be able to spread traffic among a lot of paths. So let's say your network looks like this. It would be really nice if when S sends a packet for D, it can choose any of the R1s, you know, R1B, R1C, whichever one it finds convenient. And then that guy can choose any of the R2s, and that can choose any of the R3s, and then it can get to D. And if you think about it, you know, the source can actually get a lot more bandwidth than it deserves by sort of using all these multiple paths. So it seems like the network would perform a whole lot better if you structure it so that there's a lot of different paths that it can choose from. And, you know, and so you would like to spread your traffic around as much as possible to make use of all of these different links. So various strategies for being able to use all of those paths as well as keeping things in order is that, well, switch R, its forwarding table says I look up the address or whatever I'm looking up, and I get a set of ports. Any of those are fine. So in this topology, R1A would say to get to D, I can send it on any of these 5 ports. The ports are R2A and so forth. Now, in order to keep it in order, what's traditionally done today is that the poor switch has to not only look at the envelope of the, you know, that it's supposed to look at, like the IP header, if it's an IP router, it has to go and parse all the rest of the packet too, to say, oh, this is a TCP packet. Oh, where does TCP put its ports? Oh yeah, it puts its ports here. And so it wants to kind of hash as much of the packet as possible so that it can choose different paths for different flows, but it makes sure that all the packets for the same flow go the same way. So it has to pick all these fields out of higher layers in the packet in order to determine it's for the same flow, and then it does some sort of hash so that, for instance, if it had 3 different possible ways to get to the destination, it takes the hash mod 3 and says any flow that hashes to this number, I will send on the 3rd choice out of the 3 choices that I have. I mean, it could have done it by remembering the first time it sees a flow. It could remember it and say, oh, let's see, which of my ports is least loaded? I will choose that one. But that takes a whole bunch more state. So instead, it tends to do a hash, and you just hope that you're spreading the traffic fairly evenly among that. And if it turns out that you weren't spreading traffic evenly, and one of them is you can change the hash and so that more flows go to different things, but you just don't do it too often because you might get packets out of order and freak out the index. Another way of doing it is that the switch's forwarding table might have only a single port to get to X, and you assign the destination multiple different addresses. So depending on which address the source chooses, that determines the fate of the packet. That determines the entire path that the packet will take. And InfiniBand tends to have that, that philosophy of you give a destination multiple addresses. And likewise, if you were to send it on an MPLS path, it would be kind of, you've chosen the path at the source. Okay. Recently, people have come up with a thing that they call an entropy field, which is something, you can think of it as the source does the hash on the TCP ports and the source address and things like that, and puts that field into the envelope that the switches need to look at. And this saves the switches work because they don't have to go and parse inside. The source has done the work for them, and they can use that field for doing the load, you know, for deterministically sending things for the same flow. The same way. The source also, if it has, you know, different sub-things that it's saying, sub-flows that it's sending to the same destination, and it doesn't care whether they're out of order with respect to each other, the source could purposely choose different values of the entropy field so that that source can load split its traffic to the destination. So now, another concept, so we've talked about labels and addresses. Another concept is where your forwarding table is based on flows. So instead of your forwarding table just being a destination address, it's actually the entire flow. So you would have a forwarding table entry for a particular source destination pair, protocol type, and TCP ports. So, and this is an idea that, you know, people are proposing these days. And the claim is that it's better for spreading load, so that if there's one guy that knows where all of the flows are in the network, it can sort of carefully place all of the flows through the network to make optimal use of the network bandwidth if it has perfect knowledge of where all the flows are. Well, it seems to me that if your forwarding table is based on flows, your forwarding table is going to be absolutely huge. And there's no way that you can make your forwarding table be able to support this unless you do the ATM-like thing where you create a forwarding table entry when A wants to talk to B. And that's a real disadvantage if you don't have the forwarding table filled in. The other thing is I don't believe, and this is, I'm going to say, is an area for research, because I'm saying I don't believe, I don't know, you know. It seems to me that if you really want to spread traffic around better in the network, I don't believe that flows sort of start up all of a sudden at a certain bandwidth and stay at that level of bandwidth for like hours. It seems like flows, especially at these speeds we're talking about, are extremely bursty, and congestion is kind of the result of lots and lots of things all talking at once. That just happen in their little burstiness to collide at the same time. It seems like a switch is in a better position to be able to look at its own queues and decide which one to send it on, rather than some central thing that kind of has knowledge of where all of the flows are. Yeah, it would be better if it didn't have to keep things in order, but even if it does, it can still change the hash so that to move flows around. If it seems like that would be a better way of making of spreading the traffic around than by assuming that one node that knows where all the, who all is talking to who all. Now, there might be some cases where, some applications where it really is true that all of the flows have a very predictable, stable amount of bandwidth, and then that might be a good approach. But I think in general case, it wouldn't likely to be true. But I'm just saying, it seems to me, this is a great area for research, where compare how traffic can be utilized best in a network if you have knowledge of all flows versus switches making decisions just on their own state of their own ports. Or maybe it's worthwhile for the switch to find out from its neighbor how congested the neighbor is. Maybe it's good to get information from one hop away. If that's the case, what is the cutoff? Is 3 hops away, where at that point you get diminishing returns and it's sort of too far away to really be useful? I would love to know. And so if people actually have grad students that want a project to, this would be a great thing. So now, a completely orthogonal concept. And it's sort of interesting. I've been looking at the faces, expecting some people to get like really mad at some of the things I've said. So far, no one really looks mad, which is kind of cool. Because again, I'm not saying the answers. So a completely orthogonal, congestion. Do you drop a packet? I mean, if you have only so much memory and your queue gets full, do you drop the packet? Or do you do what I call back pressure, which is that when your queue gets full, you don't ever want to drop any packet. Every packet is precious. You tell all of your input ports, stop sending me anything. My queues are full. Now, if you do back pressure, it would be great if you could do it for every single flow going on. If you could separately back pressure every single flow in the network, this would be perfect. But you can't, it's not practical. So instead, switches tend to have a few what they call classes, maybe 4 classes, maybe 8 classes. But it's few enough that you have a whole bunch of different flows all in the same buffer pool. And the problem is, once that buffer pool gets full, then you have to shut off all of your input. So you can, congestion spreads. So there's kind of a denial of service attack that you can do on a network that believes every packet is precious by merely reading packets off the network slowly. Because your switch eventually gets full of packets for you, and it has to tell all the switches not to send anything for that class, in which case they get full, and so forth. So if you're doing back pressure, there's sort of 2 ways of doing it, and people tend to be passionate about one versus the other. I think they're fairly equivalent. One is credit-based, and this is kind of like the way TCP works, that every time you receive a packet, you say, and furthermore, from sequence number N, you can send me this much more. And the other is pause resume, where you say, hey, stop. And it takes a while to get the stop there, and then you say, so you have to say stop before your thing is absolutely full, and then you say, okay, you can start again, so pause, resume. So they're kind of the same thing. Credit-based is probably a little better because it probably takes less buffering. The other way people think about congestion is have some router in the middle of your net, inform the source, my queue is getting congested, and I think you're obnoxious because you sent me a packet and it's in the queue here, so don't do that. Especially if you're really spreading traffic around a lot. If congestion comes and goes so quickly, I'm not sure how useful that information is, but that's another good thing to explore. So another completely, and probably you need segments of both, because if all of your links are exactly the same speed, and you have 2 guys trying to send 10 gigabits of bandwidth to one destination, obviously you don't want half of your packets getting thrown away. So yeah, congestion is just a really hard problem that I don't think we have any terribly good solutions for. So it's something that definitely could use some, some more kind of creative thought, as well as analysis, as well as simulation and whatever. Okay, so another orthogonal thought is, where does the forwarding table come from? So you can do it with a distributed algorithm where all the nodes are kind of equal and they all cooperate to create a forwarding table, and I'll describe how that can be done. Or another thing is where you have one central node. People use different terms for this. I'll call it a fabric manager, which everyone tells the fabric manager what the topology is, what their neighbors are, and the fabric manager calculates all the paths and then distributes the forwarding tables to all the guys. So neither concept is new. People have built networks, both ways. There's also kind of this notion of separating the control plane from the data plane, which is also a very old idea, which is that how the forwarding table gets created is completely separate from how you receive a packet, look at your forwarding table, and switch it. So what is a distributed routing protocol? So what it is you plug the network together. By the way, one of the things I really believe in, because I hate technology so much, is things should be self-configuring. Just plug it together and it ought to work. And the actual human should not be asked questions like, do you want IMAP or POP? It's like, what are you supposed to do with that? So I used to really try to design everything to be completely self-configuring until somebody told me, Radio, we have a lot of customers that really like to configure things. And so then what I do now is I design things that you don't have to touch anything if you don't want. But if you want knobs, I'll give you knobs. But any setting of the knobs will still work just fine. So, that's kind of the way things ought to work. So a distributed routing algorithm. Routers somehow exchange information with each other and use it to calculate a forwarding table. So actually, yeah, this is the first time I sort of completely redid this one, and so I had no idea about timing. Does somebody who has the whole, well, never mind. I was wondering how much more I have here. What? Right, I know I have that much time. I was wondering how many slides I had. But, okay. Well, no more than me may know that, but I don't know that because it's been more than 10 minutes since I looked at my slides. So I'm just wondering whether I should skip distance vector. I think I will. I think I'll start on linkstate because that's kind of the more popular one and the one that I like better. Okay. And the real point is just to understand how you could have a distributed routing algorithm. So there's a kind of routing algorithm that I call linkstate routing, which is, oh, by the way, I will kind of crassly mention my book. So I wrote a book about, how all of this stuff works, and it's sitting up here. It's called Interconnections, if anybody wants to come look at it. So anyway, with linkstate routing, each switch is responsible for figuring out who its neighbors are. So that's easy enough. You say, hi, I'm Radio. Who are you? And you create a packet that I call a linkstate packet that says, I am Radio. I have neighbors George at a cost of 3, Joe at a cost of 2, Amy at a cost of 7, and so forth. So you send this packet that summarizes you and your neighbors, and you forward that to everybody. You flood it. And so now everybody keeps the latest linkstate packet from every other node, in which case they'll know the entire topology. So the picture, up here, there's a picture of a network with 7 nodes, and in that little picture of the network, A and B are neighbors, and the cost of the link between them are 6. So that means that A, in its linkstate packet, says, I am A, I have a neighbor B at a cost of 6, and D at a cost of 2. So everybody, all of the switches have the same database because they all keep the most recently generated linkstate packet from each other node. So this slide should be fairly self-explanatory, right? I hope. Okay. So how do you compute roots? And I've never been able to, I take pride in trying to sort of distill things down to say it very simply. I've never been happy with my description of this algorithm or anyone else's. But once I go through an example, it becomes absolutely clear, I think. So it was due to a guy named Dijkstra. And I like putting his name on the slide because otherwise I'd never be able to spell it. So what you do is this is your linkstate database up here. That's just copied from the other slide. Each node, since nobody, if I am C, I don't care how B gets to D. I only care how I need to get to each other node. So the way that I do it is I start out by putting myself on the tree, and the tree, I'm going to compute a tree of shortest paths from myself to everybody else, using this database, which is complete information about the topology of the network. And this mysterious number in parentheses is the cost from the root of the tree to this node. So since it's me, it's 0. And so now I look at the linkstate packet of the guy I just put on the tree, which is C, and I say, okay, I'm going to look at the path to each of these guys through the one that just got put on the tree, and if this is the best path I've seen so far, I will put them underneath that node in the tree with a number in parentheses, which is the total cost. So B, the best path to B so far is under C, and it will be a cost of 0 plus 2. And so, these three guys get on the tree. After I do that step of looking at this linkstate packet and putting nodes on as children here, if that's the best path so far, then I looked at the guy who has a dotted line. The reason this is dotted line, I'm not sure this is where they're going to wind up ultimately. There might be a better path. So I find the node with the dotted line with the smallest number in parentheses, and I make that solid, saying, I know this is the best path I will find to this guy, because paths that I'll be exploring will only get longer and longer. So I can make either F or B solid, and let's see what I chose. I chose F. So F, this is now the best path I'll ever find to F. So now I look at F's neighbors and say, he has C. If I put C down there, that would be at a cost of 2 plus 2, which is 4, which is worse than 0, so I won't bother with it. He has a neighbor E at a cost of 4. If I put E down there, it'll be at a cost of 6, which is 2 plus 4. And if I put G down there, it'll be at a cost of 3, which is actually better than the path that I currently have to G. So I will remove G from here and put it down there at a cost of 3, and E and G are there with dotted lines. So now I go back and I find the one with the dotted line with the smallest number and make it solid. And so now there's no ties, it's B. So I'm going to make B solid. I'm going to look at B's linkstate packet, and B has a neighbor A at a cost of 6. If I put A down there, it'll be a cost of 8. If I put C down there, it'll be a cost of 4, which is worse. If I put E down there, it'll be a cost of 3, and I guess it used to be underneath him with a higher cost. I'm not sure why that's crossed out. I could. Yeah, it was 4, so now it's 3, and so forth. So I continue on until there's no one in with a dotted line anymore, so I'm done. So this is great, pretty picture. How do I create a forwarding table? So the way I create the forwarding table is I take everybody in this subtree and I say I need to forward to that port, and everybody in this subtree and say I need to forward out that port. Okay. Yeah, actually, right. When I saw Ethernet, so I was the layer 3 architect for DevNet. Yes? Sure.
Then you have a forwarding table for node C.
You mean if you are C?
Yeah.
Okay.
You have created a forwarding table, that's a distributed table, but now you in reality have created only a forwarding table for node C.
Oh, absolutely. Each node does their own computation. And the forwarding table that each node calculates will be different from the forwarding table anybody else calculates. Because the only thing C cares about is what port it should send things to for a given destination. You know, C might send something for a destination at port 7 with respect to C, but F would have a totally different port to send it to. So indeed, every node makes its own calculation of a forwarding table. Yes. And by the way, you can do ties. If it turns out that there's, you know, several different ways that you could put the same node in with the same cost, you can just create a forwarding table entry that gives you a set of ports. And perhaps I should have done that in this example. So anyway, I was doing layer 3 with routing algorithms and all that, and along came the Ethernet. And so I said, oh, goodness, here's a new kind of link that the routing protocol that I've been doing would not be very efficient with if you had 100 nodes on a link and they're all neighbors with each other, because the overhead of this algorithm is proportional to the number of links. So if you assumed an Ethernet was a fully connected kind of thing, you'd explode the number of links. So for that, you know, I did this little thing that I call pseudonodes, which is that if you have an Ethernet, instead of thinking of it as fully connected, you instead create one extra node, which isn't a real node. So all the routers on the link kind of elect one guy to be, you know, what I called a designated router, and it's responsible for giving a name to the link. And everybody else in their link state packet just says, let's call that Fred. So they all say, oh, I have a link to Fred. And the guy who's the master, who got elected the master, says, I'm attached to Fred, but he also issues another link state packet as if he were Fred, saying, I am Fred, and I have this many neighbors. And that's a whole bunch smaller of a link state database than if everybody reported everybody else in their link state database. Okay. So, yeah, I talked about this. So now let's compare having a central fabric manager distribute the forwarding tables versus a link state routing algorithm. It seems to me that if a link changes, with link state routing, as soon as you notice the link is down, you flood information about that outwards from the link so that it gets information about that link going down, gets to every other node as quickly as physics allows it to happen. And each node that sees this information that the link has changed can immediately update their own table based on that information. With the central fabric manager, when you notice a link has gone down, the fabric manager doesn't know this. You have to tell the fabric manager the link has gone down. And that's assuming that your path to the fabric manager still works. But at any rate, once the fabric manager knows that the link has gone down, it has to redo this calculation on behalf of every node in the network and distribute new forwarding tables to every single one of them. And that seems like recovery after a link change has got to be more quick if it's based, you know, if you're doing link state distributed routing algorithm rather than a central fabric manager. But, you know, it would be worth studying. How much are you giving up? How much are you gaining? So one belief is that if you have a central fabric manager that calculates all the forwarding tables, the switches will be a whole bunch cheaper. I'm not sure I believe that. I think that the reason switches are expensive is how you engineer them to be able to move so much data so quickly, as opposed to having this computer sitting there that can actually calculate the forwarding table. Another thing is people say, well, you know, wouldn't it be nice if you can have one place where you can affect what routing looks like in the network? So if you decide you want to change it a lot, you only need to tell one place to do that. And yes, you could do that by modifying the costs of the links. Yes?
Sorry, the central fabric manager, is that an SDN controller?
Well, people have different names for it, right? Notice I haven't used any of the buzzwords here. Yeah. Actually, afterwards, when I'm not being recorded, if you want to kind of chat with me, I will have things to say. But you know, here it's just sort of like, let's just take a deep breath and what really is new, and you know, how do we compare things rather than, yeah. So all the examples that I see, you know, in papers, like for a while there was this fad called active networks that said that, wow, you know, if we want to have like play around with wild and wacky ways of moving our packets around, we should put code in our packets to say the way I want to be handled is do this code, which seemed very odd to me. But that kind of died out. But the examples that people give are, well, suppose you want to route based on delay or you want to route based on bandwidth. Well, you can do that with a distributed routing algorithm by changing what the costs of the links are. So you can influence that. I don't know whether you need to do anything more dramatic, or if you do want to do much more dramatic things, I haven't seen examples of those as much. Now, there certainly are cases where you may want to lock down one path because one customer has paid for a certain amount of bandwidth, and by golly, they're going to measure it periodically to keep you honest. So you really have to reserve bandwidth. So you can do that for a few paths that you lock down, and that wouldn't be done with a distributed algorithm because the switches don't know how much you paid and who, whatever to get this. So that would be something that would be controlled probably centrally. But, it seems like the base computation of the forwarding table it seems like, the distributed algorithm would probably work better. So another dimension is, when do you fill the forwarding table in? One is that you fill the switch's forwarding table so that whenever they see any packet, they'll know immediately what to do with it. The other thing is, when a new flow starts up, then you ask the fabric manager to create a path for that flow. So it seems to me that proactively is better so that you don't incur the problem of the latency when you first start sending packets. It would be nice to be able to just send right away, I would think. So now this one is sort of very mysterious to me. How do you manage a network? So years ago, I've never paid too much attention to network management things. When people say the word MIB, I immediately start getting sleepy. When I try reading these things, it's like, oh. So I just assumed that I'm glad other people are worrying about that. But I assumed that networks were managed the way the original vision of management was, which was that there was one central place, a NOC, Network Operations Center, where there was a big screen, and 30 years ago I went to a NOC and it looked just like that. There was a room with a beautiful screen that showed the whole network with different colors of the links depending on how congested they were, and they were blinking if they were broken or whatever, and some human that typed mysterious commands at this one console that I assumed were reasonably user-friendly from the point of view of the network manager, and these commands would get turned into some sort of language for managing the switches. And so the language I kind of assumed people were using was SNMP. I don't care. You can use any language you want. It's good if everybody speaks the same language. And every time anybody creates a new protocol, they have to define a MIB for it, which is something that describes which parameters are readable, which are writable, what kind of things generate events to go to the NOT. And I just assumed that's how things were done. And to my, when people were saying, this is a great vision, I was saying, isn't that how things work? And they were saying, no. The way that it actually works is you basically telnet to each switch and do some sort of a horrible command line command to it in the language of that particular switch, which is like horrible. How did the world ever get to be that way? And so I've been trying to, get good answers on that. And people would say, well, various vendors come up with proprietary features, and either they don't want to divulge them in order to either you blame the vendor by saying, well, they didn't want to divulge it so that we could manage these things through the MIB, or you can blame the standards body by the vendor saying, no, the standards body refused to let us put this in there until they met for years and years and had some committee modify it anyway, and so they would not. So, so that's sort of been the unfortunate thing, that it's people have which is kind of sad. So if we were to redefine the vision at this point, there's sort of no particular reason why you have to reinvent a language for talking to the things, but whatever, if you have some language for talking to them and a certain set of things that you manage, is there any reason to believe that the world will be stable enough so that forever everything will be managed this way, or will the same thing happen where vendors come up with proprietary tweaks that you can't manage that way, so you have to telnet over to them and type commands? So I don't know. Okay. So now a new topic is, what is layer 2 versus layer 3? Why on earth are we forwarding things at layer 2? And so yeah, it's extremely confusing, to talk about this unless you know the history. So here, I'll talk about the history of IP, Ethernet, and Trill. So Ethernet was intended to be layer 2, and so I saw Ethernet as another kind of link, but it was so widely hyped that everyone got confused and thought it was instead of layer 3. And so I actually tried to argue with people who were trying to build applications directly on Ethernet, saying, no, you still need layer 2. And they would say to me, oh, Radia, you're just upset because no one needs your layer anymore. And I said, but you may want to talk from one Ethernet to another. And they said, our customers would never want to do that. So I kind of lost the battle. They built these applications. Yeah, so the story of Ethernet was, here's what the packet format looks like. You have your data, you put it in an envelope with 6-byte destination address, 6-byte source address, plus there's things like virtual LANs and protocol type. What exactly is Ethernet? Now people think, oh, Ethernet is like wildly successful. No, it died out decades ago. The thing that was actually invented. There's something else that we're calling Ethernet, but it has nothing to do with the magical invention and what all the papers were written about. So the original papers were based on this thing called CSMA-CD, which, by the way, I notice I have ingrained in my brain, and I cannot bypass it. And so at meetings, I'm at a real disadvantage, because CS means you listen and you don't interrupt when someone else is talking. Yeah, CS is carrier sense. Don't talk if someone else is talking. MA is be aware you're sharing the wire, so don't use up all the bandwidth. CD is listen even while you're talking in case somebody else, happens to talk at the same time. So, yeah. And there's lots of papers about how if you try to load it more than 60%, then you lose so much bandwidth due to collisions that, you can only get up to like 60%. It's also limited in terms of the number of nodes, maybe 1,000 nodes, maybe limited to 1 kilometer or so. But Ethernet hasn't been CSMA-CD for decades, and I still get people, telling me that Ethernet can only handle 60% of the bandwidth of the link and stuff. And also that it doesn't scale and all this, and they can find reputable papers saying that, but it has nothing to do with reality because that's not what Ethernet is anymore. So the way it got evolved to spanning tree was, as I said, people left out layer 3. And a router can't forward an Ethernet packet. A router, a layer 3 thing, needs the end node to cooperate and implement the same layer 3 protocol that the router expects to see in the envelope. So I was in a bad mood about all this around 1983 when my manager said, Radia, you do these distributed algorithm thingies. We need to invent a magic box that will sit between two Ethernets and let somebody on one talk to somebody on another. And it's like, that's a router, but of course it only works if the end node cooperates. So the constraint that we had was, given that we had all of the end nodes, a whole bunch of end nodes that implemented Ethernet only, and then the application, how could we get a box that would move Ethernet packets around, and we were not allowed to touch the Ethernet packet in any way. We couldn't change a single bit in there, and we couldn't add an extra header because there was a hard limit to the size of the thing. So that was where we came up with the basic concept of the transparent bridge, or the spanning tree bridge. So the basic idea is this, this box here, or green circle in this case, listens to every single packet. And when it receives it, it looks at the source address in the Ethernet header, remembers which port it saw that source address on, and so it learns that A is on this port. And then it looks at the destination address and says, do I know where the destination is? And if it does, it forwards onto that port. If it doesn't know where the destination is, for instance, if A sends a packet with destination J, then it says, okay, A is on this port. I have no idea where J is, so I have to send it on both other ports. So that's the basic idea. But it only works if there's no loops. If there's multiple ways to get to the same source, or if there's a loop, packets will just keep going around. So it was important to somehow create an algorithm where you just plug the thing together. And again, these green things are Ethernets. This is a port. And these, the round things are bridges. So you want to just be able to plug this together, and somehow the bridges talk amongst themselves and decide which pathways, which ports to go into backup state. They're still there physically, and in case a link or bridge goes down, you might need to use it, but you won't actually forward data along that. So when A transmits a packet, it'll go this way to get to X, which you might think, gee, that's kind of a silly path if only the spanning tree algorithm were smarter. The spanning tree, spanning means reaches everybody, tree means no loops. And you might think that if you had come up with a better spanning tree algorithm, it could have chosen different ports to turn off so the paths would be better. But no, it's once you have one shared tree, some people are going to be unhappy. And the easiest way to think about it is if you have a big circle, which is your topology, the spanning tree has to chop it in one place, and people on either side of that have to go around the long way. So, yeah, so the story of this, which turned out to be an incredibly trivial algorithm. So I spent more time writing the poem that's the abstract of the paper than I did writing the, designing the algorithm, which I did in one night, or writing the spec, which I did in 2 days. So, I have to show off my poem. So the poem is called Algorhyme, because every algorithm should have an algorhyme. I think that I shall never see a graph more lovely than a tree whose crucial property is loop-free connectivity. A tree which must be sure to span so packets can reach every LAN. First, the root must be selected. By ID, it is elected. Least cost paths from root are traced. in the tree these paths are placed. A mesh is made by folks like me, then bridges find a spanning tree. So that's basically how the algorithm works. And this is just a cute story I like to tell, which is that when I did it, you know, and especially after you come up with a poem, you really want to see the thing deployed. But the implementers were resisting. They wanted to build the simplest possible device, because after all, it was just a kludge until people were able to put layer 3 back into their end nodes. So, so I'm very bad about fighting for things. So I didn't fight at all. I just said, here it is. And it turned out that my manager fought and told them they had to implement it. So, you know, as trivial as it was, it did make their device more complicated than if they just said, look, don't put it in loops. If you put it in loops, it won't work. But then we sold the very first bridge, and I found out this story after it happened, was the world's most sophisticated networking customer, had the world's simplest topology, which was 2 Ethernets, and the salesperson was saying, it's just going to work, just put the bridge there, it'll just work. And they were saying, but we're doing all this complicated, sophisticated stuff. And the salesperson said, it doesn't matter what you're doing, it'll just work. And so they had the world's simplest topology, plugged it together, and it didn't work, and they were really angry until the field service people went to find out what they had done, and they realized they had done that. And the spanning tree was actually working perfectly. It said, I don't need to forward packets, so I won't, but if I ever do, I will. So if they could get that wrong, it's nice to put it in. So, right, as I said, there's a problem with the spanning tree, which is that your paths will be suboptimal, and you'll have some links that are not used. So why not just use IP routers? People all have IP in their stacks these days. Why are we still using this stuff? And the answer, which is something that you would never guess from most networking books, that, you know, nothing else ever existed than TCP/IP, and it's awesome in its perfection. IP is actually not a very good layer 3 protocol. Just like English is probably not a very good language, but, you know, trying to convince people to switch to something else is going to be hard. And, you know, if afterwards English tends to be the one that is the one language that survives, you can't try to analyze what was bad about the other languages and what was better about English. It really has nothing to do with the relative quality of the languages. But the problem with IP is that with IP, every single link has its own block of addresses. So if you move around, you have to change your address. Also, every router has to be configured to know which block of addresses are on which ports. And this is extremely annoying to have to do. With Ethernet, spanning tree, you just plug it together and it all works, and that's sort of nice. Now, as it turns out, IP works that way. That doesn't mean layer 3 has to work that way. And there was another layer 3 protocol around that time, which was done by ISO, the International Standards Organization, that when we were doing DECnet, we said, you know, we need bigger addresses. Why not adopt this thing that looks perfectly good to us rather than invent our own format? And so that was, ISO called it CLNP, for Connectionless Network Protocol. And it had a 20-byte address. And the way the address worked was that you could think of the top 14 bytes being a prefix that gets you to an entire cloud, as opposed to IP, where your prefix gets you to a single link. Here it gets you to a fairly large cloud that with a flat address space, where all the nodes in the cloud share the same prefix. And you can move around within the cloud. The routers keep track of where each individual end node is. So within the cloud, you don't need to do any configuration of the routers. Just somebody has to tell one of the routers what the 14-byte prefix is. But other than that, you just plug it together and it works, and nodes can move around. So, but because we didn't, with hierarchy, if you have one prefix per campus, you can have a fairly large thing, move around, keep your address. You don't have to configure these guys. Whereas if you're doing it like with IP, every link has to have its own prefix, and if you move around, you have to change your address. So, the single worst decision ever made in the history of mankind is, is that in 1992, people said, you know, IP addresses are too small. Why don't we use these 20-byte address things that were done by ISO? Imagine if we had said, oh, okay, that seems fine. How easy it would have been to move the internet to bigger addresses in 1992. You know, it was just this little researchy thing. Now it's, you know, people say, when will we have IPv6? And it's just so much harder to do this major disruption. You know, plus IP, out of kind of necessity, has invented DHCP and NAT and a bunch of other things that make it easier to live with it, and the longer we live with it, the harder it is going to be to convert. But worse yet, you know, is IPv6 dramatically better than CLNP? I don't see it, you know, especially because IPv6 has the same problem as IP, that every link has its own block of addresses. So people will still want to have some sort of, you know, cloud with a flat address space. So that's kind of why they're using Ethernet. Ethernet looks to IP like a single link. So it gives you a cloud to move around in, you know, that would have come for free as part of layer 3 with CLNP. But they don't want the limitations of spanning tree. So given that we're stuck with IP, the next evolution is TRIL, and there's a working group in IETF there. It stands for Transparent Interconnection of Lots of Links. The concept of that is that, and I feel that things should be evolutionary. So you should never tell the world, oh, I have a better idea, throw everything that you have away and replace it with these new things. The way TRIL works is you can take a spanning tree Ethernet, replace any subset of the spanning tree switches with TRIL switches, and the more you replace, the better bandwidth you'll get. So the concept is that these TRIL guys create a network where they just find each other. So if two TRIL switches have a bunch of Ethernet switches between them, they find each other and they pretend they have a link just between themselves. So you create a network that consists just of the TRIL switches. They do a linkstate protocol between each other so that they all know how to reach each other, and they create a forwarding table that says how to reach each other TRIL switch. And so the first guy that sees an Ethernet packet from an end node puts on this extra header, which is the TRIL header, which says, I am R1, I am the first TRIL switch. I want it to go to R2, which is the last TRIL switch. And that guy removes the TRIL header and out pops an Ethernet packet. So A and C don't even know that anything funny was happening, you know, versus a regular Ethernet, except it'll work better. So what does the TRIL header look like? It says who the last switch is, who the first switch is, and a hop count, and the original packet. And the switch addresses are 2 bytes long, but it's done with auto configuration because you're using this nice linkstate protocol where you send a packet that says, I'm Radia, I have these neighbor TRIL switches, and you forward it to everybody. You use that to also claim a nickname. So you say, I'd like to be 42. And you look at everybody else's linkstate packets and you hope nobody else chose yours. If somebody else chose 42, then depending on your long address, your unique address, one of you gets to keep it and the other one has to choose a different one. So, so this header is very small, it's only 6 bytes, and it's a dense address space. so that your forwarding table can just do a direct lookup. 16 bits is sort of a nice number in that 64,000 is probably big enough for the total number of switches. You can have a lot more end nodes than you have switches, but also it gives you a nice size for the forwarding table. You can have 64,000 entries and just do a direct lookup. Okay, the advantage of the extra header there, why do we need this extra header? It means that the switches inside the cloud only need to have a forwarding table which is as big as the number of switches. They don't need to know where all of the end nodes are. And the outer header is like a layer 3 header. It has a hop count, so you can do anything you do with layer 3. You can do shortest paths, you can do multipathing, you can do traffic engineering. Now, how does R1 know that R2 is the correct last switch? And this is orthogonal to the rest of Trill. You could do it a bunch of ways. At least the first deployments are doing it kind of like a bridge, where if R1 doesn't know where it is, it sends it through a tree. And when somebody decapsulates a packet, only the edge guys need to know where the end nodes are. When he's decapsulating a packet, he says, first switch was R1, the source address in the Ethernet packet was A, so if I want to send something to A, I need to send it to R1. So the edge guys need this extra table of where the end nodes that they're talking to reside and which switches they're attached to. Okay, and another orthogonal thing is who is putting this Trill header on it. So for evolutionary reasons, if you don't want to change the end nodes, it's convenient if the first switch does. But you could make a virtual, a hypervisor, or the virtual machine, or the actual application could put on the Trill header. Now, you don't want to have each one of those have a nickname, because that would sort of use up nicknames too quickly. But the switch that the hypervisor is attached to could let the hypervisor know, this is my nickname, so feel free to do the encapsulation yourself. Use my nickname rather than trying to claim another one. Okay, so you can read that. That's in the slides. That was a version of the poem that my son wrote when I asked him to. He was familiar with the first poem because my daughter's a musician. I'm her piano accompanist, and so we were doing a concert of, she was singing opera, and so there were all these Italian and German arias, and so my son, for fun, set Algoron to music, and so that was one of the arias that she sang. So I called him up and I said, hey, can you come up with a version of it that's for this new technology? And he did. So anyway, recently, oh, and by the way, it's in the spec as well, so I think that's cool. When I asked him, I said, you have 1 hour to do it because I need to go to sleep. I'm flying tomorrow to give a presentation. If you do a good enough job, I'll include that in the talk, and if not, all you've done is wasted 1 hour of your life, and you owe me that much. So he did a great job. So anyway, recently a bunch of similar things have been invented, NVGRE and VXLAN. And the way to compare them, I mean, they're really the same as Trill, as far as I can see. That you have this inner cloud that you want to have a flat address space with. And so the variations are either you have Ethernet as the flat address space, or you have IP as the flat address space. And it seems to me Ethernet is a better flat address space because it's a bigger address and a smaller header. And everybody knows how to get global unique Ethernet addresses, whereas if you're using an IPv4 address as the flat address, that will take some amount of configuration. And you're not getting anything for having a smaller address because the header itself is bigger. The other thing is the outer shell. With Trill, you have this 6-byte header. With NVGRE and VXLAN, it's some variant of an IP header and UDP header and stuff like that. It seems like the Trill header is a better outer header because it auto-configures the 2-byte switch addresses. You don't have to configure it, and it's also a much smaller header, and also the guys inside can do a very simple forwarding table lookup based on the 2-byte address, whereas if it's an IP thing, then it's a, you have to do a hash or a longest prefix match. So now this, I was just kind of thinking, suppose you compare CLNP with the 20-byte address with the 6-byte on the bottom versus IP plus trill. With CLNP, you wouldn't have needed to do this ARP protocol. With ARP, once you get to the final link, you then have to say, hey, what's your layer 2 address? And you have to keep a table there. With CLNP, it would basically be in the packet. But on the other hand, there's actually advantages to having IP plus trill instead of CLNP, which is that inside the cloud, you can build, the forwarding tables of the guys inside the cloud are only the size of the number of switches rather than the number of end nodes, and the forwarding table is easier because it's just the 2-byte lookup. So, okay, the last orthogonal thought. Oh, I'm doing great on time. Maybe I wouldn't have if I'd gone through distance vector, which is another cool thing, but at any rate. I'm always happy to be stopped in the hall and talk about things. Either if you want to sort of argue with me about things that you think I wasn't fair about something, or I've missed something, or I've gotten something wrong, or you have more insight into why management has changed so much or whatever, please do talk to me. But yeah, so the last orthogonal thought I thought I would throw in is sometimes people care about latency, which is how long does a packet get to take from the to go from the source to the destination. So one way to make it get there faster is to do what's called cut through instead of what's called store and forward. With store and forward, a switch has to receive the entire packet before it can start forwarding. With cut through, as you're receiving it, as soon as you realize which port it needs to go on, you can start forwarding on that port before you finish receiving it. So cut through is a good thing to do. But suppose you want to do cut through. What field in the header is the thing you need to look at? Well, it tends to be the destination address, in which case you want to see it as quickly as possible so that you can look at the destination address, look through your forwarding table. Let's look at the IP header. The IP header has all of this stuff in it, and the very last thing is the destination address. Sort of I imagine some sort of committee meeting where they're sitting there writing on a board all sorts of things people would want, and as they're wrapping up, someone says, oh, we should put in a destination address. And they go, good idea. Let's look at the IPv6 header. Same thing. The absolute last thing in the header is the destination address. And another little thing where people kind of made a mistake is the TCP. With TCP, you have a checksum that covers the data as well. When you're sending a packet, if you're receiving data that you want to send, you can't start sending it until you see all of the data and can compute the checksum. So yeah, that kind of impacts latency. So parting thoughts. Don't believe anything about technology X unless there's a plausible inherent reason for it. So if someone says, for instance, Ethernet is higher latency than InfiniBand, it's like, well, do I understand anything about one versus another that would make that true? And actually, there's kind of a whole story behind that. The answer is no, the bits on the wire shouldn't make any difference. But at any rate, also don't get carried away with buzzwords. Sometimes a new buzzword appears, and everywhere you look, you just see it everywhere, and people are all excited, and they say, oh, it's so exciting to be born at this point in history when this put-in buzzword, is going to transform the planet. It's like, don't get excited unless you really know what it is. And then, of course, apologies to people who've heard the story before, but it's a great way to end a talk. In my book, I try to put in these little anecdotes to make something tangible. I call them real-world protocols to explain, tangibly why, like what scaling is about or whatever. this is an absolutely true anecdote that will forever cement in your mind why it's important to know what problem you're solving before you try to solve it, because that's a real problem in this industry. People just roll up their sleeves and start looking at special cases and do that rather than kind of taking a deep breath and trying to figure out what the real problem is. So anyhow, when my son was 3, he ran up to me crying, holding up his hand, saying, "My hand, my hand." So I kissed it a few times. "What's the matter, honey? Did you hurt it?" And he said, "No, I got pee on it." So anyway, there'll probably be time for some questions in the room. And other than that, thank you. Yep.